Let me welcome you once again to yet another interesting topic under um, relations and function. Okay, in our previous studies, we looked at the various types of relation, the various types of mapping. We are now on what functions. Okay, we have already talked about evaluating functions. This time, we are going to look at how we can prove algebraically what a one-to-one function is, and that is what we are going to do. All right, but in the first place, what is one-to-one functions? We have already talked about this. Yes, we have already talked about this. So let me quickly remind you, or let's go through so that you can recall what we said about one-to-one function or one-to-one relation. As the name suggests, one-to-one, meaning that when you have only one element of the domain corresponding to only one element of the codomain. That is where only one element of the domain has a unique image of the codomain when only one. Okay, yes, we have already looked at it, but this time we are going to look at how algebraically we can prove that a function is one-to-one, and that is what we are going to do in today's lesson. Okay, so without wasting much time, let's quickly dive into what is before us. All right, great. So to show that a function is one-to-one algebraically, what we are trying to say is that whether each element or one element in the domain will correspond to what? Only one element in the codomain. Okay, so that is what we are just going to do. Okay, all right. Now let's also note that when we say one-to-one function, we can also say it is called what? Injective function. Yes, injective function. Okay, so injective, we mean what? 1 to 1. All right, so in a question, if I ask you to show that a function is injective, know that you are to prove that it is what? 1 to 1. Okay, so that is another term that we can use. All right, great. So let's quickly look at it. Now, when we say a function is one-to-one, algebraically, a function can be one-to-one if and only if, okay, if and only if we have this. So let me take you through this. So I'm taking you through this. Now we are saying that function f defined by f such that a maps onto b is one-to-one if and only if. So for algebraic proving, a function can only be what? One-to-one if and only if we have this function at a is equal to the same function at what? B, which implies that a should be equal to what? B. Okay, so this is what the algebraic proof of a function being one-to-one. Okay, what does this mean? It means that whenever you are given a value to substitute, okay, a value of the domain to substitute for x in the relation, when you substitute that value and you are also given another value which is also b, if you substitute this value also into the same function, at the end of the day, the answer you get must be what? A equal to what? B. Anything other than this ceases to be what? A one-to-one function. Okay, so when you are asked to prove or show that a function is one-to-one by algebraic proving, this will prove or show that that function is what? 1 to 1. So we shall not waste much time. Now let's take an example, or let's solve some examples, okay? So that we see how it is done. All right, let's take our first example. All right, so let's look at these two examples. Okay, good. So we are to show whether or not the following are what? 1 to 1. 1 to 1 algebraically. So let's begin with our solution. Okay, all right, great. So algebraically, to show that a function is 1 to 1, then f at a should be equal to f at b, which implies that a should be equal to b. So it means that if you take each function or each relation, when you substitute this, you are going to get this. Okay, that's what we are going to do. So let's look at a, which is given as f at x is given as 2x plus what? 1. That means my x should be equal to a, and then equate to what? My x should be equal to b, and solve. Okay, so we are going to put these values and equate to each other. All right, so it means that here I will substitute a here. Wherever I see x, I will put a there. So I will write my 2a here plus 1 should be equal to the same 2, and this time my x is what? B plus 1. Yes, because that is what the proving is saying. Okay, so if I multiply this by that, I'm getting 2a plus 1, which should be equal to 2b. Okay, 2b plus 1. I can multiply terms. I can maintain this here, and write 2a is equal to 2b plus 1. I'm just transposing this one here, which will be -1, so that at the end of the day, this one will go. All right, and then I'll have 2a is equal to 2b. From here, I can divide both sides by what? My 2, where the 2 will go, these 2 will go, then I can have a is equal to b. All right, so once you realize that now the proof is true, once you get this, because that is what algebraically it is saying, and now once we have gotten a to be this, then we conclude that therefore f at x equals 2x plus 1 is 1 to 1. Very simple. All right, good. Now let's look at the b part. Let's see the b part. So for my b, I will have this. Okay, great. So the b is also given as h at x is equal to 1 divided by x plus 2, where x shouldn't be equal to what? 2. So there is a condition. The condition is saying that x shouldn't be 2, so that if you should it's supposed to be -2. Okay, let's go back to the question. Yes, this is supposed to be -2. Okay, so it means that if we should put -2 here, the entire thing will be what? Undefined, and that is not what we are looking for. Okay, because that's why this condition is given. So let's quickly follow the same proof. It means I'm going to substitute my a for x here and equate to, when I substitute what? B. So this time I'm going to have this a plus 2 should be equal to 1 on b plus 2. So this is what? Equation of fractions. Okay, involving what? Expressions. All right, how do we do this? Some one will say you do cross multiplication, which I don't know where they get that crossing multiplication from. We can just find the LCM. What would be the LCM? The LCM is, so let me find my LCM. LCM is giving us what? So looking at this, we can get the LCM as A plus 2 and what? B plus 2. This is my LCM. So how do I do it? I will just multiply the LCM through. Okay, I'll multiply the LCM. So here I can have A plus 2 and then B plus what? 2 times 1 on A plus 2, which is equal to the same A plus 2 and then B plus 2. Okay, I know you say it's a long process. No, it shouldn't be a long process. That's the right thing to do. Okay, all right, great. So, and divide by B plus 2. Good. So I will just look at which ones are common here. This one and this one is common. This one and this one is common. Which I will be left with is, I'll multiply this by this, which will give me what? B plus 2. Okay, is equal to, and it's left with this one. A this times that also gives me A plus 2. I can maintain B here, which is equal to, and transpose 2 there, which will be this plus 2 minus what? 2. Now this is positive, this is negative, so I'm going to get B is equal to A. Now, because all these are what? Positive. These ones are positive. I can just what? Bring the A here. I can bring A here and bring what? B here. So this one also suggests that A is equal to B, which also what proves that the function is 1 to 1. Okay, so I can just write, therefore h at x is equal to 1 on what? X plus 2 is 1 to 1. Okay, let's solve one last example on that and see. Okay, so we are going to solve another example on this one. Okay, so we shall solve more examples in our next videos. Okay, all right, good. So let's solve 2 or more examples in our next videos. All right, so let's end here and do the other examples in our next videos. So watch out for the next video, what we are going to look out for. All right, okay, so see you in our next video. Thank you. Bye bye.